In the far reaches of our solar system, beyond Neptune's orbit, something peculiar is happening. An enigmatic force is affecting icy bodies, causing groups of these objects to have unusual orbits that can't be explained solely by the known planets. Scientists theorize that this may be due to a large hidden planet, often called Planet 9. First suggested in 2016, this potential new celestial object has fascinated astronomers. Interestingly, this isn't the first time a planet has been proposed using mathematical predictions. Neptune and Pluto were both discovered because their gravitational effects were predicted before they were visually detected through telescopes. Astronomers observed anomalies in Uranus orbits and later in the Kuiper belt objects, leading to the discovery of these distant celestial bodies. A century later, we are in a similar situation with Planet 9, continuing this intriguing tradition of using mathematical predictions to discover hidden planets. Some researchers speculate it could be a wandering planet captured by our sun's gravity, while others think it might have formed from the same gas and dust disk as the other planets. If Planet 9 exists, it is believed to be 10 times more massive than Earth and orbit the Sun at a distance of 400 to 800 astronomical units, AU, which is 400 to 800 times the Earth-Sun distance. Astronomers have been diligently searching for evidence using advanced telescopes and sophisticated computer models to track its influence. After years of skywatching, solving mathematical equations, and running complex computer simulations, they now have the most compelling evidence yet that Planet 9 truly exists. This revelation adds an exciting twist to the story of the hidden planet. So, what evidence did researchers uncover in their search for Planet 9? Despite discovering exoplanets hundreds of trillions of miles away, why has it been so difficult to directly detect Planet 9 in our own celestial neighborhood, despite using some of the most powerful telescopes available? Although Planet 9 was first proposed in 2016, its story began shortly after the discovery of Uranus in 1781. Over time, astronomers noticed something strange. Uranus did not follow the predicted path exactly. It showed accelerations and decelerations in its orbital motion, suggesting the influence of an unseen force. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch-Adams in England, independently hypothesized that Uranus' irregular movements could be due to the gravitational pull of an undiscovered planet. They used complex mathematical calculations to predict the possible location of this invisible celestial body. This was a bold hypothesis, relying solely on mathematical calculations to propose the existence of an unknown celestial object. Le Verrier sent his predictions to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant aimed their telescope at the part of the sky specified by Le Verrier. To their surprise, they found Neptune on their first night of observation. This was a remarkable achievement, marking the first time a planet had been discovered through mathematical prediction rather than serendipitous observation. After Neptune's successful discovery in 1846, astronomers believed they had identified all the major planets in our solar system. However, when they tracked Neptune's orbital path, they noticed small irregularities similar to those observed with Uranus. These irregularities were subtle but persistent. Given the success of predicting Neptune's existence based on gravitational influences inferred from Uranus' orbit, astronomers wondered if a similar method could reveal another celestial body farther out. This quest led to the discovery of Pluto. Over 8 decades later, on February 18, 1930, Clyde Tombaugh, a young astronomer at Lowell Observatory, spotted a faint distant object moving against the background of stars, confirming the existence of a new celestial object. Initially hailed as the long-sought Planet X, Pluto was later found to be much smaller than expected. Pluto's mass was too small to account for the gravitational anomalies observed in Uranus and Neptune's orbits. This suggested the existence of more unknown objects beyond Neptune's orbit. In 1951, Dutch-American astronomer Gerard Kuiper proposed the idea of numerous icy bodies beyond Neptune, with Pluto being just one member of the larger belt of objects now known as the Kuiper belt. The first direct observational confirmation of Kuiper belt objects, KBOs, came in 1992 when astronomers David Jewitt and Jane Liu discovered 1992 QB1, a small icy body beyond Neptune. This discovery confirmed the existence of a group of objects in the region Kuiper had predicted. As more objects were discovered beyond Neptune, the term Trans-Neptunian objects, TNOs, was adopted to describe all objects orbiting the Sun beyond Neptune. TNOs represent a broader category that includes any minor body in the solar system orbiting the Sun at an average distance greater than Neptune, 30 astronomical units or more. The discovery of Sedna in 2003 added to the intrigue. Sedna, another large TNO with a very elliptical orbit, has a perihelion closest point to the Sun of about 76 astronomical units and an aphelion farthest point from the Sun of about 936 astronomical units. In the years that followed, more extreme trans-Neptunian objects were discovered. There is a distinct peculiarity in the orbital patterns of TNOs. Imagine scattering dozens of marbles on a flat surface. Normally, you would expect the marbles to scatter randomly. However, if many marbles cluster oddly in a specific area, it might suggest a powerful force or factor pulling them together. This scenario is similar to what scientists have observed with TNOs. Their orbits do not scatter randomly but show clustering. If TNOs were orbiting randomly, their paths around the Sun would be spread out in all directions, like the marbles in our analogy. Their perihelion points would be scattered across the sky, not clustered in one particular area. However, their perihelion points tend to cluster in a specific part of the sky. This clustering is highly unusual, suggesting a common factor influencing their orbital paths. Additionally, the major axes of their orbits, the lines connecting their closest and farthest points from the Sun, show alignment that is statistically unlikely by chance. This alignment provides strong evidence for the hypothesis that an external force, possibly the gravitational pull of a large unseen planet, is at work. The consistent alignment of these orbits is compelling evidence supporting the idea that Planet 9 exerts its influence from a distance, shaping the orbits of these distant objects. Building on the discoveries of Sedna, Eris, and other TNOs, the hypothesis of a distant, unidentified Planet 9 gains significant traction. In January 2016, astronomers Konstantin Batygin and Mike Brown published a groundbreaking paper that further solidified this hypothesis. They examined the orbital paths of 6 distant TNOs, suggesting that these configurations could be explained by the gravitational pull of a previously unknown planet. They proposed that this hypothetical Planet 9 would have a mass about 10 times that of Earth and orbit the Sun in a highly elliptical path ranging from 400 to 800 astronomical units. The discovery of Neptune happened quickly. Astronomers found it on the first night of searching based on mathematical predictions. However, the hunt for Planet 9 has been much more challenging. 4 main challenges arise. First, its great distance. Planet 9 is believed to be 10 to 20 times farther from Earth than Pluto. At such a vast distance, the planet would receive very little sunlight, making it nearly invisible against the starry background and difficult to spot with current telescopes. Second, the possibility of Planet 9's orbit being very elliptical adds to the challenge. This means it might spend most of its orbit in the farthest and darkest regions, far from the Sun's light. Consequently, it would appear even fainter and harder to detect during these extreme orbital phases. Third, the large area of the sky where Planet 9 could be located makes the search difficult. This extensive search area requires careful scanning of large sections, requiring repeated rechecking and confirmation of observations to avoid missing anything. Finally, Planet 9's slow movement across the sky makes detection efforts more complicated. Due to its great distance from the Sun, Planet 9 moves slowly relative to the background stars. This slow movement requires long and repeated observations to distinguish it from the background stars. Astronomers must carefully track potential candidates to confirm they are moving objects, not stationary stars. Given these challenges, simulations play a crucial role in the search for Planet 9. Simulations allow researchers to model complex systems and predict behaviors that are difficult or impossible to observe directly. Let's explore how researchers use simulations to provide the strongest statistical evidence for Planet 9's existence. The orbital paths of TNOs are not stable over long periods. Over time, Neptune's strong gravitational pull can perturb their orbits, scattering them widely or even ejecting them from the solar system. This dynamism means that TNOs are constantly changing, often crossing Neptune's orbit. To explore this further, A research team conducted simulations based on the initial conditions proposed for the formation of the inner Oort cloud. The Oort cloud is believed to be a distant spherical shell of icy objects surrounding the solar system, extending from about 2,000 to 100,000 astronomical units from the Sun. They selected TNOs with perihelia greater than 30 astronomical units and semi-major axes ranging from 100 to 5,000 astronomical units, resulting in a simulation of 10,000 particles. The research team conducted 2 sets of simulations, one including the hypothetical Planet 9 and its proposed position, and another without Planet 9. The results suggested that Planet 9 could affect the orbits of TNOs through the direct action of the Runge-Lenz vector. This vector describes the shape and orientation of an orbit under the influence of a force like gravity. Its direction defines the orientation of the ellipse, while its magnitude is directly related to the orbital eccentricity. A Runge-Lenz vector of 0 corresponds to a circular orbit, while non-zero values indicate elliptical orbits. Planet 9 can elongate these orbits and change their inclination. The simulations showed that without Planet 9, fewer TNOs come close to Neptune. Notably, without Planet 9, the number of TNOs coming close to Neptune drops significantly as the distance from the Sun decreases, peaking around 30 astronomical units. Conversely, with Planet 9, these close encounters happen more consistently over a broader range of distances, starting from around 16 astronomical units. To validate their findings, the team conducted a statistical analysis, comparing the observed patterns in the simulations with real-world data. They accounted for observational biases and compared the simulation results with 17 known TNOs with perihelia under 30 and semi-major axes greater than 100. The comparison strongly supported the model including Planet 9, showing a significantly higher probability of 0.41, compared to just 0.34 for the model without Planet 9. This large difference in probabilities indicates that the model with Planet 9 better matches the observed behavior of TNOs, suggesting a significant role for Planet 9 in shaping their orbits. In the coming years, the Vera C. Rubin Observatory in Chile will begin operations, featuring a powerful 8.4-meter telescope capable of conducting nightly wide-field surveys of the entire sky. This observatory will use insights from recent studies, including those proposing the existence of Planet 9, by carefully tracking the orbits of distant TNOs. If these objects consistently show patterns of close encounters with the Sun beyond roughly 16 astronomical units, as predicted by the Planet 9 model, it could be a crucial indicator of the elusive planet's presence. This combination of advanced technology and cutting-edge research holds promise for deepening our understanding of the solar system's outer reaches. Ultimately, it may lead to the long-awaited confirmation of Planet 9. Recently, the James Webb Space Telescope measured the rate at which the universe is expanding. The findings have highlighted a critical point in cosmology, revealing a fundamental flaw in our current understanding of the universe. If you missed this development, be sure to catch up on the exciting discovery. If this video has taught you something new, please remember to like and subscribe to our channel for future updates. See you in the next installment.